All right, so this is chapter 22, neutron stars and black holes. These are the problems that we're going to do. We're not doing all of them. Let's start with the first one. It says the angular momentum of a solid body is proportional to the angular velocity of the body times the square of its radius. Use what's called the conservation of angular momentum. I'll show you what that means to estimate how fast a collapsing stellar core would spin if its initial spin rate were 1 revolution per day. All right, and its radius decreases from 10,000 kilometers to 10 kilometers. Okay, so that's the basic idea. So we're going to this this particular picture. So this is these are the problems that we're going to do in chapter 22, 1, 2, 3, 4, 6, and 7. Okay, so that's so here's I know big L we've normally used as luminosity, but in physics it's also used as the angular momentum. Okay, so sorry about that, but we're not going to do that many angular momentum problems, so don't worry about the fact that in this one problem L stands for angular momentum. Normally in astronomy we'll use capital L as luminosity. Anyhow, so they give us the radius, and actually it's the change in radius, and they give us what omega is, the initial omega. So omega is what's called the angular speed. So let's look at this picture right here. You have something that's spinning. It's spinning about some axis of rotation. So r is the distance from the axis of rotation. Omega is the rate at which it's spinning, or another way of saying it, that's the angular speed. And so the idea of this thing called the conservation of angular momentum, I didn't write out all of the word momentum, sorry about that, is that the angular momentum, the initial angular momentum, so L sub I equals L sub F, the final momentum, final angular momentum. All right, so that's the basic idea, and that's how we're going to solve this problem. All right, so this is the basic setup. We're going to use this, that the angular momentum, the initial angular momentum, L sub I, is equal to the initial radius of this this rotating dead star squared times the angular velocity, which is omega initial. And so that's going to equal the final angular momentum. So we're basically, it's r final squared times omega final squared. So you set those two things equal to each other. They give us in the problem that the initial angular velocity is 1 revolution per day. All right, and we're going from a size of 10,000 kilometers to 10 kilometers. Remember, this thing is collapsing in on itself. So it's just like an ice skater pulling their arms in as they're rotating. They're going to start to spin faster, and so our job is to figure out what omega final is. That's the whole idea. All right, so we're just setting these two equations equal to each other. It's really easy, and so we get r final squared omega final, remember that's what we're trying to solve for, is equal to r initial squared times omega initial. All right, so we can rearrange that equation and solve. It's pretty simple. You just divide both sides by r final squared, oops, and then so this becomes r final squared, and of course the r finals on this side cancel, and so that this is solving for omega final. All right, so let's put the numbers in. All right, so it's going to be remember the numerator and the denominator with the r they're both squared, so I can just square the whole thing. So it's going to be 10,000 divided by 10, right? Because that's the final. Let's see, yeah, it's 10 divided by 10, and they're 10, and they're both kilometers, so the kilometer part cancels. Remember, we got to square that, and then we multiply by 1 revolution per day, 1 revolution per day. And so this thing's going to speed up enormously. Let's see, what do I get? I get 1,000,000, so 10 to the 6th revolutions per day. All right, but we'll try to make a little bit more sense of that. All right, so let's try to and in thinking about neutron stars, right? A neutron star has a radius of about 10 kilometers or so. Remember, that's the one. Remember, we compared it to the size of Manhattan, the Manhattan Island in New York, of course. All right, so we determined that the final angular speed is 1,000,000 revolutions per day, but it would be nice if we had that in a little bit better units, more like units of rotating neutron stars. And so in one day there are 24 hours, so the days cancel, right? So the days cancel, and then in 1 hour there's 60 minutes, so the minutes cancel. The hours cancel, and in 1 minute there are 60 seconds, so the minutes cancel. So basically, you take 1,000,000. You divide it by 24, you divide it by 60, you divide it by 60 again, and you get the revolutions in, so you get the speed in revolutions per second, right? So that's really what we want. And so that comes out to be, what did I get? 11.57, roughly, 11.57 revolutions per second. All right, so this thing is spinning very, very fast. When it collapses from 10,000, rotating at 1 revolution per day, and then it goes from a radius of 10,000 kilometers to 10 kilometers. It'll speed up its rate of rotation to 11.5 revolutions per second. All right, let's do number 2. All right, for number 2, basically, they want you to get this, the idea of density. So it says, what would your mass be if you were composed entirely of neutron star material and the density was 3 times 10 to the 17th kilograms per cubic meter? All right, so when you read this, right, what they're actually asking you is, you gotta make sure you read these things. What would your mass be? So in other words, mass equals question mark. So, and then we're going to assume that the average human has a density of about 1,000 kilograms per cubic meter, which is pretty typical. That's about the density of liquid water. Compare your answer to the mass of a typical 10 kilometer diameter rocky asteroid. All right. So let's do that problem. Okay, so let's change here. All right, here we go. All right, so remember the density equation, right? We use the symbol rho for density is equal to mass divided by volume. All right, and so you got to choose a particular mass. So a typical I don't know. I'm just going to pick a mass of 100 kilograms. All right, so that just makes life a lot easier. So if somebody had a mass of 100 kilograms, that'd be somebody a little bit more than 200 pounds, for example. So I mean, it doesn't really matter. All right, so if the mass was 100 kilograms or whatever the mass would be in kilograms, you could, and you know that the human body has a density, that's supposed to be a rho, of 1,000, right? Remember, it's kilograms per cubic meter. Then, of course, you could rearrange this equation here, and solve for the volume, right? So what would be the volume of a human being, the average human being, all right? And of course, to measure that, right, you'd put yourself in, you'd completely immerse yourself in water, note the position of the water before you immerse yourself, and then the position of the water after you, after you immersed yourself. All right, anyhow, the volume here is the mass divided by the density. All right, so the mass is 100 kilograms, sorry, I'll put the kilograms, divided by 1,000 kilograms, which of course cancel right away per cubic meter. All right, and so the kilograms cancel, and so 100 divided by 1,000, of course, is just 0.1, and so the 1 over cubic meters, the cubic meters comes up to the numerator, so it's 0.1 cubic meters. That's about the, anyhow, that's the volume. Why do we need that? Well, they give us the density of a neutron star as 3 times 10 to the 17th, right? So the density of the neutron star, this is a neutron star, and is 3 times 10 to the 17th kilograms per cubic meter. So if to figure out the mass, right, you stick with this equation. The mass of somebody would be equal to the volume that they take up, right? Now their volume isn't going to change at all. They're just saying, okay, what if the person was made completely of neutron star material, which would be impossible. They're just trying to give you a sense of, how much more this person would weigh. I mean, that would be another way of doing this problem. That's not what they actually asked. All right. So anyhow, it's 3. The mass is equal to just bring the volume over to the other side of the equation, and so the mass is the volume times the density. I probably should have wrote that. Anyhow, 3 times 10 to the 17th times 0.1, right? Times 0.1. All right, and I'll put the units in just a bit. Well, of course, in the units, right, the kilograms per cubic meter, the cubic meters cancel, right, because the volume's in cubic meters. Anyhow, this is still 3, but now because it's times 10, times 0.1, it becomes times 10 to the 16th, kilograms. All right, so now as far as here, hold on, let me set up the next part. So for part B, they ask you, how much is this compared to like an asteroid? All right, so they give us the rocky asteroid, and so a rocky asteroid, by the way, I'm gonna use the same density as the rocks on the surface of the Earth, which is about 3.3. All right, so, or 3. Actually, you could use 3 or 3 point. I think when I did it, I did 3.3. Anyhow, all right, let's finish this problem number 2. So we calculated that a human, the average human or something, or actually this was more like a guy. Anyhow, it doesn't really matter. The mass would be about 3 times 10 to the 16th if they were made of solid neutron matter. Made of neutron material. And so they want us to compare the mass to the mass of an asteroid, right? So an asteroid, let's say, has a density of or the typical rocky density of 3.3 kilograms per cubic meter. The diameter of this asteroid, so let's say it's spherical, is 10 kilometers, so the radius, of course, would be half of that. The radius would be 5,000. The radius would be 5,000 meters. Right? We want to actually do this in meters, and so the volume of this asteroid, all right, I'll say V sub A. That stands for the asteroid. Is going to be 4 pi divided by 3. Remember, anything that's spherical always has the same equation. All right, so then 5,000 meters, and you have to cube that.